Hello friends, in this lecture I would like to explain another important example, that is cantilever beam. So already I solved previously singly reinforced rectangular beam, doubly reinforced rectangle beam and T beam. But comparing with these three models, this cantilever beam is very simple. So just in the singly reinforced beam, what is the difference between this cantilever beam and this singly reinforced doubly rectangular beam means? See here, so this is singly reinforced beam means here we have to provide tension reinforcement in the bottom side. So this is tension reinforcement, and we are providing two hanger bars in the compression side. If it will be doubly reinforced beam means, what we have to do, we have to provide compression reinforcement in the top side and tension reinforcement in the bottom side if it will be doubly reinforced beam. Then if it will be cantilever beam means, what happens? So for cantilever beams we have to provide tension reinforcement on the top side and hanger bars on the bottom side. So this is the difference what we have to observe. So for singly reinforced section we have to provide tension reinforcement in the bottom side. For doubly reinforced section, tension reinforcement in bottom side, compression in top side. But for cantilever, just reverse of the singly reinforced section. If it will be singly reinforced, doubly reinforced means top side tension, bottom side compression. That we have to remember. And see the data what is given in the example. They will be given clear span of 2.5 meters, working live load of how much it will be, working live load of 20 kilonewton per meter, and cantilever beam is monolithic with RC column means column. So the beam is like this, in column connection with the beam like this. So it is cast connection with column and beam. So like this, and column of wide 300 mm. So the column wide is around 300 mm. Here RC column 300 mm wide means the beam is of 300 mm wide. So that is, for example, if you see here, this is the beam portion. So I'm drawing the cross section of the beam. So they will given the data, this one, the beam is of 300 mm wide and 450 mm deep. Okay, then coming to the next step, FCK will be equal to 20 Newton per mm square, Fi will be equal to 450 Newton per mm square. So write down B will be equal to 300 mm, capital D will be equal to 450 mm. So already based on this capital D, you can provide a effective depth, that is removing some cover, bottom cover, sorry, for cantilever beams you can take from top because tension reinforcement is on the top side. So removing some cover like 50 mm, so remaining part will be around 400. So like that D can be provided 400 mm. Otherwise you can check for span to depth ratio. Span to depth ratio for the cantilever beams will be 7. So if you can see in the codal provisions, so the cantilever beam will be 7. Here already we solved so many problems regarding simply supported, which is L by D of 20 span to depth ratio, but here cantilever it will be 7. So you can take down that 7 here and you can solve. What is the span given? 2500 by 7 equal to D. If you simplify, how much you will get? 2500 by 7, it will be around some 357 mm. So whatever the value you will get, we can provide approximately some 360 mm. But if you take 360 mm, it will be too long. So therefore, you can provide effective depth will be 400 mm. Like that also you can take, or else you can check with span to depth ratio also. So your adapted D will be equal to 400 mm. Then go to the next step, which is loads. So loads means always first find out dead load. Dead load in the sense self weight of beam. So already we know that. So this is the beam. So here how you will calculate the dead load? First this B and this capital D and this 1 meter span. So the beam length we are taking for 1 unit into its unit weight, means B into D into 1 into unit weight of RCC. What is B? So B will be given 3 meters, which is 0.3 in meters, 300 mm. D will be given, capital D will be 435, 0.45 into 1 into its unit weight, equal to 3.375 kilonewton per meter. And what about live load? So live load already given in the question, 20 kilonewton per meter. Here plaster finishes, floor finishes, if you want you can take 1 kilonewton per meter, or else if they will given any data in the question you can add that one. Otherwise you can assume 1 kilonewton per meter and we can add here directly. Otherwise no need. So here finishes I will take 0.625 kilonewton per meter. Actually it will be given in the data. I will take as it is. Then total working load. Total load. So I am taking here. Total load will be equal to, if you add all these, 320 plus 0.6 around 24 kilonewton meter. So this is total load. If you want ultimate load, you can take multiples of ultimate load 1.5, which is factor of safety, that is 24 kilonewton per meter. If you add the multiply this one, you will get 36 kilonewton per meter. So entire procedure will be same like as previous one only. So after getting this ultimate load, we know that next step is movements. So movement for cantilever beam will be WL square by 12. Sorry, WL square by 2. For simply supported beam, it will be WL square by 8. But for cantilever beam, ultimate moment will be equal to WL square by 2. So already we know that one will be equal to around 36 W and L will be equal to 2.5 whole square by 2. If you simplify, you will get around 11 2.5 kilonewton meter. Then what about VU, which is shear, equal to W into L. That one will be equal to 36 into 2.5. That one will be equal to 90 kilonewton. Sorry, it is only kilonewton. So this is the procedure for finding moment and shear. So already we know one condition. We find mu less than mu limit. Already we designed this problem based on the singly reinforced section. Mu greater than mu limit. We designed this problem based on the W reinforced section. but for T-beam the concept will be different. But here for cantilever also, first check that condition whether you will get mu less than mu limit or mu greater than mu limit. For checking that one, your limiting moment, your limiting moment will be equal to, whenever Fe4 for Fe415, your mu limit will be equal to 0.138 FCK BD square. That one will be equal to 0.138 into FCK will be given as 20, B will be 300, D will be adopted depth 400 square. So take down all the values in terms of meter. If it will be in terms of meter, simplify, you will get 132 kilonewton meter. So here it will be Newton per mm square. Then you will get 10 to the power of minus 6. If I am taking all the values in terms of kilonewton meter. Why? Because 20 kilonewton to meter, 20 10 to the power of 3, 300 in terms of mm to meter. Okay. Then if you find out these two, what you will get? You will get the value of mu less than mu limit. Why? Because already we seen that your mu will be equal to 112.5, which is less than 132 kilonewton meter. Here your mu will be less than mu limit. You can design this section based on the singly reinforced section, which is under reinforced section. If it will be greater than, means you can design doubly reinforced section. Already we solved that procedure in the doubly reinforced section. Same like that only, you can provide tension reinforcement, compression reinforcement. For that you can check shear and deflection. But here your section will be based on the singly reinforced section. After obtaining this mu, for that mu you can provide the area of the steel. So already we people know that as per the codal provisions, what is your value? See here, what is the formula generally using? This is the singly reinforced section, means we are providing the reinforcement in the tension zone only with this formula. So take down the formula as it is, providing reinforcement, which is tension reinforcement. So that is mu equal to 0.87 Fi area of the steel into D 1 minus St Fi by V into D into Fck. So this is the general formula. So already we have all the values. In the same way we can calculate this problem. That is, what is your mu value? Your mu value will be around 112.5 kilonewton meter. I am taking terms of mm. That is 0.87. Fi will be 415. So here your area of the steel is unknown, into 400. Again 1 minus area of the steel into 415 by B value will be equal to 300. D value is 400 into Fck is 20. So here you can find out the area of the steel by simplifying with your calculators. You will get area of the steel around 928 mm square. So this is the required area of the steel. So in the same sense, already we solved 3 problems how to calculate n number of bars. So if you are watching continuously, here you will get a clear idea how I am solving this problem. Again I will show you the procedure. N equal to, means number of bars. I am talking about number of bars that one will be equal to capital AST by small ast. This is the general procedure what we are using. So first I will come with the dia bar, which is 20 16th dia bar. See here, I will come with 16th the dia bar. So n number of bar will be equal to n. AST required will be capital AST will be 928. Small AST will be 5. Dia will be 16. 5 16 square by 4. If you simplify, you will get approximately equal to 5 bars. So check area of the steel with that 5 bar. Area of the steel will be equal to 16, sorry, n into pi d square by 4. That is n is 5 into pi 16 square by 4. So around you will get 1004.8 mm square. Means if you are using 16 dia bars, we required 5 number of bars. Means for 5 number of bars, we required 16 dia bars. Your area of the steel will be 1004.8 mm square. So required will be 928. Provided will be 1004.8 is okay. Provided will be higher. Again check with some more trials. 20 dia bars. So n will be equal to 928 by pi 20 square by 4. How much you will get? You will get around 2.95 bars, which is approximately equal to 3. So if you check with the area of the steel, 3 into pi 20 square by 4, how much it will be? It will be around 942 mm square. See here, your required area will be 928. If you provide this bar means comparing with this one, it will be economical. Why? Because if you provide 3 bars of 20 dia, area of the steel will be 942, which is greater than required but economical comparing with 5 bars of 16 dia. Therefore, always compare like this. Go to 2 more trials. Like that, you can conveniently see provide 3 bars of 20 dia. So therefore AST what we are provided here 942 mm square. So this is the procedure, generally we opt for that one. Similarly, provide 2 hanger bars. Provide 2 bars. For minimum 4 bars will be required to support any beam. Already 3 will be providing bottom side and 2 minimum requirement in the compression side. 2 bars of some 10 mm or 12 mm dia. 12 mm dia. We have to provide in the compression phase. Okay, so 10 mm also required. 2 bars of 20, sorry, 20 will be higher. 12 mm dia also required, no problem. Then after providing this one, immediately go for the shear calculations. Shear reinforcement. So I think this problem will be very simple comparing to the previous one. So as per the what is the procedure shear reinforcement? So see the formula which was in code number 72. Nominal shear, this is tau v will be equal to Vu by Bd. Okay. So provide shear reinforcement, tau v will be equal to Vu by B into D. What is Vu? 90 kilonewtons, which is 19 to the power of 3. B value will be 300. D value will be 400. Approximately how much you will get? 0.75 Newton per mm square. And what about tau c? So here already I told you so many times. Check the conditions. Tau v less than tau c, tau v greater than tau c, and again less than tau c maximum, or tau v greater than tau c, or greater than tau c maximum. So this is the first case, this is the second case, this is third case. Third case happens, you can go for redesign. First case happens, you can go for minimum shear reinforcement. Minimum shear reinforcement already I solved in singly reinforced section. If you will get minimum shear reinforcement, this case you can see singly reinforced section in our channel. Okay, if you are in second case, already I solved this case in doubly reinforced section and T beam also. Okay, you can check both the problems for the reference how I will solve these two. And now also I am showing for this case, but we don't know now itself how which case you will get. Before that you can calculate tau c. So if you'll get this third case, you can go for redesign. Okay, then for finding tau c, you can check the problem. So calculate tau c, permissible shear stress in concrete. See here, this is the table which is used to calculate permissible shear stress. For calculation of this one, so this formula will be required. So this is PT. So how it will be? PT will be equal to 100. Area of the steel will be 942 by B into D. 300 by 400. It will be around 0.785. So PT will be equal to 100 area of the steel by B into D. 100 942 by 300 by 400. So how much you will get? You will get around 0.785. So if your PT will be 0.785, check in the codal. 0.785 will lies between 0.50 and 0.75. Okay. So for M20 grade concrete, it will be 0.30 and 0.35. So here, write down somewhere for 0.50, it will be how much? 0. Sorry, for 0.75, it will lies 0.75 and 1.1. So 0.75 and 1. I will write here. For 0.75, how much? And for 1, how much? We want 0.788. So for 0.7y, it will be 0.35, and for 1 it will be 0.39. 0.35 and 0.39. Sorry, actually I am looking in the table number 23, but you can follow table number 90 for design strength of the concrete. You can see table number 90. I will show that one. So table number 19 in page number 73. Write down here. You please follow this one. Page number 73 in IS 456 2000. So table number 19. Okay. So this 0.785 will lies between 0.75 and 1.00. What is the value for 0.75 for M20 grade concrete? It will be 0.56, and M for 1 it will be 0.62. So it will be 0.56 and 0.62. We want 0.785. So this is general procedure only. Each and every time I am telling that you can draw a scale like this. No need to remember the formula for this one for making interpolation. So always remember in like this only. So for 0.75 it will be around 0.56, and for 1 it will be around 0.62. So how much the, so I am dividing the form of triangle and rectangle. So wherever you can take the triangle rectangle, it will be same, and the difference of these two will be 0.06. And again I want the value around 0.785. 0.785. So here entire rectangle wherever you can take, it will be 0.56 only, but here we want this difference up to here, this position, means take down these two similar triangles. One will be this one, another one will be full length span, this one and this one, by taking two similar triangles. First see the difference, 0.75 minus 1, it will be 0.25, and take the difference 0.75 minus 0.785. From here to here it will be around, how much it will be? It will be 0.085. So it will be 0.085. So by taking two similar triangles, this one and this one, we want this value, and for this full triangle already the x value will be 0.06. Like that you can take. So if you want to do that one, so for this full span of 0.25 the value will be 0.06, and for 0.0 this range 0.85 the value will be around x. If you cross multiply you will get x value will be around, so I simplified, I will get 0.0084. Already this x value will be 0.0084, and bottom there will be some value which is 0.56. You can add that one, 0.56. So which is 0.5684. So directly you can take 0.57, or else if you are not interested in simplifying, you can take the value which is very near, 0.75 or 56 Newton per mm square. If you find somewhat difficult how to evaluate this, means you can take direct value which is tau c will be equal to 0.56 Newton per mm square. And so here we will get one confirmation, tau v will be greater than tau c. So which was lies in second condition. Why? Because it is not lies in first condition, but it is lies in second condition. Again check with tau c maximum. Tau c maximum will be M20 grade concrete 2.8. So we will get this one which was in table number 20. So here this one will be 2.8. So for that you can get one confirmation. Here tau v will be greater than tau c and less than tau c maximum. So here according to this condition it was lies in second case. So whenever it will lies in second case, you can design the shear reinforcement as per IS, which was given here. See here, find out stirrups based on this formula, that is 0.87 Fi ASV d by SV, and where VUS will be equal to VU minus tau C into BD. Here find spacing SV value. So already I solved these models also. First take down the formula which was given in the code book, that is SV will be equal to 0.87 Fi ASV d by VUS, where VUS will be equal to VU minus tau C into BD, where VU will be equal to 90 kilonewton, which is given, minus tau C will be equal to 0.56, B will be 300, D will be 400. So all the values we can take down in kilonewton. So it will be 10 to the power of minus 3. You will get around 23 kilonewton. Then substitute this value here. You will get SV will be equal to 0.87415 into, what about ASV? You can take ASV. So provide stirrups of 2 bars of 8 legged 8 mm. Already we know MS bar starts with 6 mm diameter, which is mild steel plain, and HYSD bar starts with 8 mm, like that. So here I am using 8 mm, and 2 legged in the sense if there will be 4 bars, you can connect the bars like this, so which is 2 leg. So here I am using 2 legged of 8 mm stirrups, which is pi d square by 4 into this d value is around 400, by VUS will be the 23 kilonewton, which is 23 into 10 to the power of 3. So if you simplify, you will get SV value will be around 631. Means your spacing will be getting higher value. So according to the codal conditions, we know your SV does not greater than 0.4575D. 0.75D. See here, if condition here it will be given or not. You can, if it will be given in the codal's provisions, you can follow that one. Otherwise, you can remember the formula. Check once with the code book. So it is around 0.75 into some 400, which is 300 mm, and the condition one more will be SV does not greater than 300 mm. So here, after finding spacing based on the formula, you will get SV will be equal to 631 mm. But according to our condition, it as per IS, your spacing does not greater than 300 mm. So provide minimum. So your spacing does not greater than 300 mm. If your SV will be equal to some 250 means you can provide that only according to the formula. But whenever it will be greater than this formula, you can restrict the value to the condition which is does not greater than 300 mm. So write down the statement. Provide two-legged 8 mm stirrups at a spacing of 300 mm center to center. So after finding this one, immediately check with the deflection. Check for deflection. So we know the formula for deflection, that is L by D provided will be less than L by D maximum. So what is L by D maximum? So we know that L by D maximum will be equal to L by D basic into KT into KC into KF. So what is L by D basic? Already I told you. For cantilever it will be 7. And what about KT? So already we provided tension reinforcement. So tension reinforcement in the sense, check once how the tension reinforcement, page number 38. See here, the tension reinforcement will be provided by using the formula, that is 0.87 Fy, 0.58 Fy means 415, area of the steel required to the top, area of the steel provided. So how the area of the steel required, how much we want. So you know that your area of the steel required will be 928 mm square, and provided will be how much you provided, 942 mm square. So if you simplify, you can simplify the value in calci, how much you will get, take down that value. So I am simplifying here, that is around 237 curve. So 237.1 curve. So 237 curve lies between 240 and 190, like this, somewhere here, like this. So this is 230 curve, 237 approximately between I taken. And your percentage PT equal to 100 area of the steel by, so if you want these values you can find with this formula. Already we find for finding tau c. So how much your percentage of steel, it will be around 0.785, it will be around 0.785. So 0.4 to 0. Between 0.6 0.7 will be somewhere 85. So like that I am checking approximately wherever the curve touch, and exactly to that point check with right left. So how much you are getting, if you are calculating like this means you will get around 1.2 higher value, 1.2 higher value. So 1.21, this is 1.24, 1.21, 1.22, like that. Somewhere I am taking K2 will be equal to 1.22, like that. Approximately I am taking some value which is 1.22. See here I am writing 1.22. And what about compression? So here we are talking only singly reinforced section. So singly reinforced section you only get KT. So if you are solving doubly reinforced section, you will get Kc also. If you are solving T beam or L beam, you will get Kf also. But these two will be not there. So you better omit, or else you can keep 1 and 1 also, no problem. Simplify, how much you will get? 7 into 1.22. You will get around 8.54. So your value will be 8.54. Check whether L value will be L by D. How much L by D you provided? Clear span of 2.5, depth of 0.4. So how much you will get? 2.5 by 0.4. So it will be 6.25. So you provided 6.25, but minimum required will be 8.54. So here whatever you provided is lesser than the maximum what required in the beam. So therefore your deflection is safe. Then for the cantilever beam, after completion of this one, again one small topic will be there, which is development length. So development length is also important for the cantilever beam. So I will show what is development length. So development length will be in page number 42. So just to calculate that one by using formula. See here, development length of bars. The development length is given by LD equal to diameter sigma s by 4 tau BD. So the formula will be the development length of that sigma x will be equal to 0.87 F5 dia by 4 times of tau BD. So actually the formula will be like that. So the formula will be given here. Dia sigma s is 0.87 F5. The design strength of stress in bar at the section considered design load. So that one will be LD equal to 0.87 F5 dia by 4 times of tau BD. Why the sigma is equal to 0.87 F5? Already I told you while drawing stress strain curve. So in the starting itself, in the basic concepts, that is 0.87, Fi is 415, dia bar. So this development length. So what are the bars you are keeping? So we are keeping 3 bars of 20 dia. That dia we have to take in here by 4 times of tau. What is this tau BD? Again check with the code. So for the tau BD, design bond stress. So the development length includes anchorage value of hooks in tension reinforcement. Again, they will given one condition. The tau BD for M20 grade concrete will be 1.2. And for deformed bars conforming IS 1786, these values shall be increased by 60%. So it will be increased by 60% means 100 plus 60 means 1.6%. It will be increased. For bars in compression, it will be increased by 25 means 1.25%. But here we are talking only about tension reinforcement. So for M20 grade concrete, your tau BD will be equal to 1.2 and it will be increased 60 point means 1.2 into 1.6 times. So that is 1.2 into 1.6 times. So if you simplify this one, you will get 940 mm. So I am just simplifying this one by using the formula simply. Okay, the concept behind development length and anchorage bond will be very wide, which will be coming in gate point of view. But while solving the design, that is how much time we will take for this one is just some 2 to 3 minutes enough. Just take down the formula and find out the development length. I will show you the purpose here. What is the development length means? Here, this is the detailing of the reinforcement. So the beam you are observing here, this part will be the detailing of the reinforcement. I will explain each and every part. First, coming to the point. So the beam, the width of the beam will be 300 mm, and effective depth taken from the top of the reinforcement to the bottom extreme fibers, which is 400 mm, and overall depth will be 450 mm. And in the bottom zone there will be two hanger bars. These two will be hanger bars, two hanger bars of 12 or 10 dia. So this will be two hanger bars. I will write here two hanger bars of 10 dia or 12 dia, and here these three bars will be three bars of 20 dia. Okay. So here the bottom bars, the top bars which I am indicating here, these bars will be the tension reinforcement bars. If you cut this section and look somewhere, you will get all these things. And from the front view, you will get these round bars directly. And from the side views, you can look here means you will get this one. And this is the cross section of the beam. So this is the tension reinforcement where we are keeping top view, three bars of 20 dia. And whatever you are observing with this reading, this one will be the stirrups which we are providing, two legged 8 mm dia bar, which we are keeping here is two legged 8 dia. So I will write like this, two legged 8 dia, 8 mm dia stirrups at a spacing of 300 mm, not greater than 300 mm. So already so here I will mention spacing, one bar between another bar, and this is the hanger bar which we are observing in the cross section. So that is hanger bars of around two bars of 10 dia. Then, so this is the cantilever beam. There will be no support right side, and here there will be only support which is the column. So we don't know this column width which is given here. Based on the development length and based on the bars, you can provide some column length. Maybe approximately I am taking here some 450 or 400 mm, this one. And so already we calculated this development length. So what is this purpose of this development length? Now I will talking about this point. See here, if we are providing any bar like this, if we are providing any bar, for example I am talking about this bar, I am providing like this with red bar. So generally if I will keep the bar like this, what happens? Whenever any load is applied, automatically what happens? Automatically the bar will bend like this. So whenever the bar will bend like this, for example the length of the bar will be some 5 meters, assume like this. Whenever it will bend, so the bar length will be automatically will spreads, means the original position of the bar will starts here, automatically it will slips its original position. Even in the beam also, whenever any loading is applied, automatically it will slips its original position, means that it will decrease the size of the bar because of the bending, then it will loses its strength. So therefore for cantilever beams, always at the supports it is very necessary to provide extra bar, means to provide development of the bar, means the reinforcement of the bar. What you people are observing here, so this entire bar where I am indicating with violet color is the development bar. So how much it will be? We calculated it will be around 940 mm. So here in this 450 beam, there is a chances of keeping only 400 mm. We are removing some space for the effective cover. and the remaining 500 mm I am bending in the column vertically 90 degrees. Like that, you can provide the bar. For example, you can take the column size as some 300 mm. You can provide 250 here, and you can extend the column remaining part into the column. Like this, you can provide the development length of the bar. So I am again explaining the amount of reinforcement bar length needed to project it into the column to provide the desired strength between steel and column. Means the development bar gives the, so this reinforcement when where we are producing this development bar, the length of the bar required to transfer this force in the bar into the surrounding concrete. This is called the development length. So the development length bar will be provided like this, and the purpose of the development length bar also I explained. So this is the procedure for solving cantilever beam. For cantilever beam, development length will be required.
Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.